Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week, our speaker is Mariia Sobchuk from the University of Waterloo, and she will be talking about the quantum independence number.
Thank you, Sabrina. Yes, that's what I'm going to be talking about. And you probably heard about independence number, and we're going to talk about the quantum independence number. So obviously, these two things are related. First, we'll see how they are related, what a quantum independence number is. And obviously, because it's a different quantity, we would like to see the examples where the two are different. So that's mostly what this talk will be focused on. The examples of graphs or families of graphs where alpha and alpha q are different. And then you can be watching out for some common theme between those examples, because in the end, we are going to find the characterization theorem that shows when alpha and alpha q are different. So a lot of this work is based on my thesis that I did with this under supervision of Chris Gottsell. Okay. Here. So this quantum graph parameters is not just a quantum independence number, it's a wider topic. And it started a bit earlier. Quantum independence number came later to the point. And for our purposes, we are going to concentrate on its definition that Manchinska and Robertson came up with in their paper, where they started viewing quantum independence number with the tool of quantum homomorphisms. And you can see the citation here is 2016, but in fact, the paper was available in 2012. So this predated those next two papers. And apparently the topic is interesting because it's obviously related to the classical independence number quantity that's well studied and of interest to many graph theorists. Also, we will see that when we're trying to understand what quantum independence number is, we're going to be using different bounds, but those bounds happen to be also bounds on the independence number. Therefore, we get some extra quantity between some known bound and independence number. So depending on that, we are going to understand something more about just classical graph. Also, in the study of the quantum independence number, a lot of interesting graphs show up. Maybe they are not new, but we definitely got a different view of them and started learning more about some graphs we have seen before. Discovered some new properties, and some of which like examples of that kind of reasoning we're going to see in this talk later. Also, we will see why those quantities are fundamentally different based on the Scarpa's example, who showed that, in fact, there are infinite families with the separation between alpha and alpha q graphs. And we are also interested in small examples that exhibit the separation between those two parameters. And one such example was found in Teresa Piovesan's thesis. The graph was relatively small and 24 vertices. So we were able to study it in more detail. Okay, and so let's see what this quantum Cochlear number is, in fact. So first, recall that we can think of the classical independence number in terms of homomorphisms. So alpha is the largest number t integer such that there is a quantum homomorphism from the complete graph on t vertices into the complement of our graph, classical homomorphism. So once we remove the word classical and put the word quantum, like Manchinska-Robertson did, then we get this quantum Cochlear quantity. But that's the general idea. When it's phrased mathematically informally, we get the following definition. So let's take a look. So quantum independence number is the largest number of columns in a matrix P. The rows of that matrix are indexed by the vertices of the graph, and the entries are projections that have to obey some conditions. So first of all, in every column, the sum of projections has to be identity. So that also implies that those projections are orthogonal. Then we have requirement that in the rows, the projections are orthogonal, but there is no requirement on the summation or anything like this. And then there is another relation between two projections in different columns I and J, and in different rows U and V. So in the case that U and V are adjacent, then we require that projections in those I and J's column for any I and J have to be orthogonal. And this is kind of related to the classical independence number, in the sense that we don't want the adjacent vertices to be in the same cochlic. So the whole matrix P is called a quantum cochlic matrix. Okay, and the quantum cochlic number is the largest number of columns we can have in quantum cochlic. All right. Okay, so let's take a look at the example and how to construct this matrix. One of the basic ideas, and maybe we'll have already done this all life before. So here's a Petersen graph, and the vertices 1, 5, 9, and 3 form a maximal independent set of size 4. Okay, so let us try to construct a quantum cochlic of size 4 and see if it's possible. So here we have 4 columns, and let us order the vertices in the cochlic by the first, second vertex, etc., and put the corresponding standard basis vector in that row. So for example, vertex 1 is the first one, say, in the cochlic, then we have this E1 vector in this row, etc. And well, did we construct a quantum cochlic in this way? Well, we certainly did a classical cochlic, but also note that the entries are dimension 1, and they are projections. The 0, 1 are the projections in dimension 1. And also in every column, clearly we have that the sum of projections is 1. In every row, again, clearly projections are orthogonal, and the only non-orthogonal entries are those ones, but we can see that whenever there's edge, say between 1 and 2, then those projections will be orthogonal as well. So P1, 1 and P2, 2 will be orthogonal. P2, 1 will be orthogonal. Good. So in fact, this is a quantum cochlic. So what can we conclude from this example? First of all, that classical cochlic is also a quantum cochlic, and we know how to get it. Second of all, because the definition of quantum independence number is includes maximization of number of columns in any of those matrices, then we know that alpha q is at least alpha. So that's a bound already. And obviously, we probably would like to have dimension more than 1 if we want the separation to occur, but that's the idea. All right, so we understand that. And then there will be later in the talk, we will take use of the definition of a quantum chromatic number. So I thought to put it here as well. Those two properties are often studied together, and so it's also good to know them. But just keep in mind, and we'll use this definition later. So what is a quantum chromatic number? Well, the same idea is that we can think of classical chromatic number in terms of homomorphisms as being the smallest number S, such that there is a homomorphism from the graph into the complete graph on S vertices. That's the classical chromatic number. But again, if we put the quantum in front of homomorphism, then we got the quantum chromatic number. A lot of things go interesting once you do that, just like you put the quantum independence number. So again, phrasing it more formally, we are looking for a quantum coloring matrix that has S columns, and S better be as small as possible. And the number and the rows are still indexed by the vertices. Again, entries are still projections, but this time we have requirement on the summation in the rows to be identity instead of in the columns like before. And we have requirement on the projections to be orthogonal in the same column if the rows correspond to the adjacent vertices. So like QVI and QUI are orthogonal because have to be orthogonal if V and U are adjacent. And again, you can think of it as an analog to classical coloring, where if we have the vertices of same color, we want them to be not adjacent. If the vertices are adjacent, we have them to be different colors. And so again, we call by analogy this matrix Q a quantum coloring matrix. Okay, so is a quantum chromatic number related to the classical chromatic number? Yes. Let us see how. So we get the analogous bound here. You can see in the title. So let's take a look at the example of this wheel graph, where which is three colorable. Say vertex 0 is colored the third color, vertices, the white vertices are first color, and the gray ones are the second color. And put the corresponding standard basis vectors in the rows. So the vertex is 0 is the third color, we have E3 in that row, and so on. So let us verify if that does indeed satisfy the definition of the quantum quantum coloring. Well, each row sums to identity, sort of the analogy that every vertex has just one color. Well, certainly if we have different kind of projections, that may not be as clear of an analogy, but you can think of it like why the definition exists there. And also in each column, the vertices corresponding to the edges, say 1 and 2, are orthogonal. So good. And that's all we have to verify. So in fact, the classical coloring also gives us the quantum coloring matrix. And now we just, again, the idea, can we get a smaller number of colors in this case? So again, because we're doing minimization now, the quantum chromatic number is upper bounded by the classical chromatic number. Okay, good. So now we understand the definitions. Hopefully, seeing some examples, it is more clear. And now, once we get this quantity, what can we do with this? How can we understand it, estimate it, etc. So that's when the bounds come in, because so far that's what was the first way to approach this kind of problem. And what is interesting here is that, as I said, some bounds that are bounds for the classical independence number happen to be also bounds on the quantum independence number. Okay, so for example, inertia bound, you probably heard of it, but the idea is that if we have a Hermitian weighted adjacency matrix of the graph, we can just estimate the number of non-positive or non-negative eigenvalues of it, and the smallest of the two will be the upper bound on the independence number. Well, Wechen and Elphick, in the series of their bound papers, in one of those papers, they proved that it's also upper bound in alpha Q. So we have this chain of inequalities. And that is nice because what we have is that once alpha saturates the inertia bound, then we know that alpha and alpha Q are the same. Also, once we know that alpha and alpha Q are not the same, then there's no saturation of this bound if you're interested in these kind of problems. And this quantities, yeah, we can get good estimates here. Also, Lovesh theta bound can be quantum. The Lovesh theta is a quantity of the graph, parameter of the graph that can be estimated, calculated in polynomial time. So this is a very good bound. Also, the same idea holds. Even if we don't have exact saturation here, it's nice that we will see how to understand what alpha Q is in that case. And also there's a ratio bound that also became quantum in the same way. So we know that if you have a k-regular graph and tau its smallest eigenvalue, then alpha is upper bounded by this quantity. And so and if it's also a bound on the quantum independence number, we get that if there's a graph that exhibits the separation between alpha and alpha q, then the ratio bound is not saturated. So if you're the person who's interested in saturation of ratio bound, then you will know more graphs to avoid in your studies. This is nice. Okay, so let us see how in practice can be used, what kind of results can be proved with them. And when you have those bounds, it's always easier to prove that alpha is equal to alpha q if there's some bound that's saturated classically. For example, with the first theorem, we didn't use any of those bounds here, but just as another classical analog of the quantum result is that if we have a graph obtained by adding an apex vertex to x, means vertex that adjacent to every vertex of x, then we cannot increase the quantum independence number, and that holds also obviously for the classical independence number. And this was interesting result because one of the graphs that exhibited the chromatic number separations was exactly formed in this way by adding an apex vertex. So it turned out that we did not change the alpha q of that graph. Also, because we are looking for the graphs that exhibit strict inequality of alpha q greater than alpha, it's also good to know when alpha and alpha q are the same. So we ignore those examples. So we proved that using inertia bound that if alpha q of the graph is 2, it happens if and only if the independence number is 2. So it's a big family of graphs to disregard if we're looking for the separations. We know Lovász theta of the Calligraph on 13 vertices, and Calligraph is just on graph and graph theory, but what matters for us is that we can get its Lovász theta, and that is just the square root of number of vertices, which is strictly less than 4 in this case. Well, at the same time, we know that the independence number of the graph is 3, and the quantum independence number is an integer. So we also get in this way that alpha and alpha q are the same in the Calligraph on 13 vertices. Okay, so these kind of results show us that alpha and alpha q can be sometimes similar and how to possibly calculate alpha q. All right, but then once we've seen those examples, we would like to move on to those that don't have that property, and alpha is strictly less than alpha q. Okay. First example will be of the infinite family that is from Scarpa's thesis. For the construction, he used the Cartesian product of graphs. So let us recall that the Cartesian product of two graphs has vertices, which is direct product of the vertices of the first graph and the second one. And two vertices are adjacent if either the first coordinates are equal and second ones are adjacent, or vice versa. So in this example, it's from Wikipedia, but it's quite convenient to understand. It's a house graph and a K2. And in a Cartesian product, we get 2 copies of K2. So for example, AX and AY are the vertices and they're adjacent because first coordinates are equal, but the second ones are in K2, so they're adjacent. Okay. Okay. In fact, it can be used for the separation in the following way. Scarpa used first the following lemma. So if we have a graph X on n vertices, such that its chromatic number is strictly greater than some number k, then once we take a Cartesian product of graph X and the complete graph on this number k vertices, then we know that independence number of that is strictly less than n. Okay, and the proof idea of this result is quite important because it is one point to this common theme that's going to reappear again and again. So the Cartesian product kk and x can be partitioned into n cliques, just a fact. But the point is, if we were to choose a largest independent set, we would have to choose at most one vertex from each of those n cliques. So that would give us upper bound of n. But what's interesting here is that we cannot choose n independent vertices from all of those cliques. There inevitably will be a pair of vertices that are adjacent. So that's why how he showed that alpha is strictly less than n in this graph. But it's also an interesting property. Once we have n cliques, we cannot choose independent vertices from each one of those cliques. Those graphs have a name that will show Kochen-Specker graphs, but that will show later. And then the separation of the infinite families can be constructed in the following manner. So like if you have a graph X such that it exhibits the separation of chromatic numbers chi and chi q, then we know that the independence number of the Cartesian product will exhibit the separation between alpha and alpha q. And that y gives an infinite family because it was already known that there's infinite family of graphs that exhibit separation between chi and chi q. So that is it. And we were not going to go in the details of this proof because this is just constructing the quantum independence number mostly. But it was interesting that the way the separation was constructed is with this kind of property. Okay, so that's one example. The next example is due to Manchinska and Robertson, and that involves homomorphic products. So let us first see what homomorphic product of two graphs x and y is. Again, the vertices will be the direct product of the vertices of x and y. And we say that two vertices are adjacent if either the first coordinates are equal or the first coordinates are adjacent and the second coordinates are not adjacent. And in the paper, Manchinska-Robertson motivate this construction, this graph product, because it corresponds to the orthogonality of projections when we are talking about quantum homomorphisms. So that's a useful product in that respect. And so let us see how it works. Okay, in this example, I have a path on 3 vertices and 2 vertices, and the homomorphic product turns out to be just like a Cartesian product. Well, that's obviously not always the case. Just because if I were to put more vertices, that would just make it a bit not so obvious what the product is. So, for example, we have here vertices A0, B0, they're adjacent because the first coordinates are adjacent and second coordinates are not adjacent, like this. So that's a Cartesian product, but also a homomorphic product. Okay, so how to construct the examples of graphs where there's separation between alpha and alpha q is possibly to Manchinska-Robertson thought that probably if there's a if quantum independence number can be phrased in terms of quantum homomorphisms and classical independence number can be phrased in terms of homomorphisms, then possibly if there's a pair of graphs that have homomorphism between them but not a quantum homomorphism, sorry, the other way around, if there's a quantum homomorphism but not a classical homomorphism, then possibly there is something we can say about their independence numbers as well. So we have two lemmas. One, the first one was known classically, and that is if we have graphs x and y, there is a homomorphism from x to y if and only if the independence number of their homomorphic product is equal to the number of vertices of x. So in fact, it's upper bounded by this, but we know that there's a homomorphism if only the inequality holds. Okay, so in the paper, they prove that also the quantum analog of this result exists mainly that if there's a quantum homomorphism between graphs, then the quantum independence number also is number of vertices of X. So that's nice, and that's an if and only if condition. Okay, so the corollary of that result is that if we have a quantum homomorphism from X to Y, but not the classical homomorphism, then the independence number of the homomorphic product of those two graphs is strictly less than quantum independence number. And that follows because of from those two lemmas. If we don't have a homomorphism between two graphs, then alpha of the homomorphic product is strictly less than number of vertices of X. While on the contrary, the alpha q of the homomorphic product is number of vertices of X. So that's a nice example of the separation here. Yes, and now we are going to move to the concrete examples with the separation. The Piovesan's graph on 24 vertices, which is an orthogonality graph. So recall that the orthogonality graph of a subset of vectors has the vertices as those vectors, with the vertices being adjacent if the corresponding vectors are orthogonal with respect to the inner product. So the GD24 is the graph in orthogonality graph of those vectors in R4. And there it is. It's a very nice graph. And it came from the paper in quantum information. So that's another connection. Lots of those quantities or bounds have connection with the quantum communication theory. Okay, so Teresa Piovesan used the graph to show that the independence number of the graph is 5, but alpha q is strictly greater than 5. So again, the colors here correspond to consecutively each next 4 vertices, but also to the cliques. And more visually here, you can check that if each of the 4 vertices in a row forms a clique, because the vectors form a basis over 4. So this graph can be partitioned into 6 cliques, just like with those colors we can see. And you can see that alpha q is at least 6. So possibly those two quantities are related. And yes, indeed. But also before I show how to get this lower bound on the alpha q, again, note an interesting property that the graph can be partitioned into 6 cliques, but we cannot choose 6 independent vertices. So alpha is equal to 5. Just like with the Scarpa's, one of the Scarpa's graphs, we have this property. We have partitioned in the cliques, but we cannot choose one one vertex from each clique, so that all of those vertices are independent. Again, so the property came to us again. And so let us see how to get this lower bound on alpha here using the partition into cliques property of the graph. So this will be easily generalizable. That's why I would like to show it here, and it's quite easy. So in our quantum Koklik matrix, for each vertex, let all the projections be 0 except one that is in the column corresponding to the clique number of that vertex. So say if the vertex 1 is, say vertex 5 is in clique 2, then in the second entry, in the second column of the entry corresponding to vertex 5, we will have a projection, one rank 1 projection built from this vector. So this vector times its transpose. So that's what we'll have for each vertex. All entries will be 0 except one corresponding to the column of the clique that vertex is in. Okay, so that takes care of the orthogonality conditions of the projections in the rows. And in the columns, we know that they will sum to identity because the only non-zero entries in the column will be the entries from the cliques. And those cliques came from the basis vectors over 4. So once we form the projections out of those basis vectors, we're going to get vectors that sum to identity. And we can also easily verify the condition of the orthogonality of projections in different columns whenever the rows corresponding to adjacent vertices. So that's in general, this construction just applies for anything whenever we have a graph that can be partitioned into n or k cliques, then alpha k will be at least k, just in the same way. Okay. All right, but what's interesting about the graph is that we found it's also a Calligraph. So Chris got to notice that it's a Calligraph for S4 with a set of transpositions, which is quite nice. And I'll just remind you what a Calligraph is, in case it's been a long weekend. So we have group G, and the vertices of the graph are elements of this group, and 2 vertices are adjacent, G1 and G2, if G1, G2 inverse is in this connection set that we defined. So in our case, the connection set is the set of elements in S4 that have order 2. Okay, and we found this by inspection, this assignment of the vertices to make it a Calligraph with transpositions. So the vertex 1 that was a standard basis E4 goes to the empty permutation, and etc. So this was kind of didn't have any reasoning behind it. It's just a lot of brute force to try to find what works. But then, if you would like to generalize this kind of example, then reasoning is important. So we indeed try to find the explicit bijection, constructed and constructive bijection between the orthogonality graph and the scaly graph. So if we have permutation, we would like to know which basis vector it goes to, which vector in R4 it goes to, that to get a bijection to the orthogonality graph of those vectors. Okay, so and when we did this, something interesting showed up. So again, note that the vertices in each 4 vertices form a clique. And what's interesting is that every next clique, when we think of a graph of permutations, is a coset of the first clique. So for example, we just take vertices in the first clique and multiply by permutation to 3. Then we get second clique. Multiply by 1 to 4, get this third clique, etc. So possibly that meant that it's a good idea to assign the vertices in the first clique to the basis vectors E1 through E4, because somehow they generate the rest of the graph, and then see what we get from there. Okay, and that's quite nice, because how would we do this? Well, we know that the vertices that in the Calligraph, the vertices that are different by transposition are adjacent. And the orthogonality graph, we know that vertices that are orthogonal are adjacent. So we would first try to write each transposition that generate the permutation group in terms of the basis vectors, and then have each permutation written as a product of transpositions, and also the product of those vectors. But we'll have some multiplication rules involved. So for example, we know that vertex with the permutation 1, 2 is adjacent to the vertex with permutation 1, 2, 3, 4, because they're different by transposition 3, 4. At the same time, vertex 3, 4 is adjacent to the vertex 1, 2, 3, 4, because they're different by permutation 1, 2. And at the same time, we already know what 1, 2, 3, 4 permutation it's a vector E2. So using this kind of reasoning, we were able to write the transpositions in terms of basis of vectors, getting us some vectors in R4. In the process, we came to these relations. Because the multiplication of the vectors was involved, and then it had to obey some rules. This is the rules they obeyed, which is quite interesting. You probably can recognize quaternions out of this. Okay. And yeah, so we were able to do this for all the permutations once we got the transpositions and got exactly the vectors in orthogonality graph. So having this kind of example, we thought, okay, can we get something for other group, permutation group, for example, S5? And yes, we were able to get it for S5, but for the larger permutation groups, there are too many degrees of freedom that show up. So that still is open. Okay. So how did we get another example from S5 that exhibits the separation between alpha and alpha Q? And well, we would like to construct the bijection again between the elements of S5 and some vectors in R4, of which there will be 120. So we already have the bijection between some kind of bijection between vertices of S4 and the vertices of the orthogonality graph of the Pivot-Sans graph. So some other vectors in R4. What is left to us are just we need to find the assignment for the permutations that didn't have number 5 in them, basically, because these ones are still not assigned any vector in R4. So we start with the vertex transposition and pretend that we assume, we assume that the other vertices 1, 5 is adjacent to are also different by transposition from 1, 5. But that's all we assumed. And then in a similar way, we were able to get the vectors for 1, 5 and other transpositions involving number 5, therefore other permutations involving number 5, and therefore all S5. And then just we got some collection of vectors, and we took 120 vectors and we made an orthogonality graph out of them. Well, it turns out that graph is not a Calligraph, because even though it contains S4 and the Calligraph of the Pivot-Sans, it doesn't exactly require that all the permutations from S5 are adjacent, either different by transposition. Only those transpositions themselves. So it's not a Calligraph, but it is an orthogonality graph, and it also has this magic property that it can be partitioned. The vertices can be partitioned into 30 cliques of size 4. But then we cannot choose independently 30 vertices, one from each of those cliques. And so we checked by computation in Sage that alpha is equal to 29, in fact, in this case. But just as we've seen before, once we have a graph that can be partitioned into some number of cliques, we have immediately a lower bound on alpha Q. So that is nice. We got one example. Once we start doing this thing with S6, then there are just too many degrees of freedom that show up, and possibly there's something to do. But you were happy with this 5 for now. Okay, so all right. So now we've seen already an example of an infinite family where alpha and alpha Q are different. Example used in construction with homomorphisms, and this one. And tangibly, it showed up in 2 cases that the partitioning in the cliques was an important property. Okay. Such that we cannot choose independent vertices from all the cliques. All right. So now we're going to move on to the generalization of this idea. And the characterization of all graphs where alpha and alpha Q are different. Okay. So first of all, the magic property that I was referring to was the property of being a projective Cox-Becker graph. So what is that? Is the graph orthogonality graph of some projections in complex d-squared dimensional space, but with the extra condition. So when we look at the cliques that are formed by projections that sum to identity, then we cannot choose independent vertices from all such cliques. So whenever we have cliques that formed by the vertices summing to identity, then we cannot get independent vertices from each of those cliques. And well, clearly, because projections cannot sum to anything more than identity, that will be maximal cliques as well. So let us see how, for example, Pio-Bessan's graph was a projective Cox-Becker graph. Well, here is its orthogonal representation, and we can easily make it into projective orthogonality graph by taking rank 1 projections of each vertex, so XX transpose for each vector. The cliques formed by the projection summing to identity are, for example, those cliques indicated here, 1, 2, 3, 4, 5, 6, 7, 8, etc. These are not the only cliques from the projection summing to identity, because the more ways we can get a basis, but this is just one example. And we've seen that before, that you cannot choose independent vertices from each of those cliques. Well, obviously, once we have projections, this still holds. So we can verify it for the remaining projections as well, summing to identity. So that's a projective Cox-Becker graph. Okay. Okay. And so the characterization that we have is similar to what Scarpa had for the chromatic numbers. And what he said is that we have the separation between chi and chi-q if and only if, once we have the quantum coloring matrix and take the projections in that matrix to be the vertices of the orthogonality graph, then we get projective Cox-Becker graph. And that's if and only if condition. So we were able to prove this also for the independence numbers. Once we have quantum Cochlic matrix and take the projections to be the vertices of the orthogonality graph, we'll get always a projective Cox-Becker graph if alpha and alpha q are different. So that's quite nice. It is not easy to check. Obviously, that means if we already have the quantum Cochlic matrix, then we can probably try to check if the graph is Cox-Becker graph. But obviously, it's hard to get the quantum Cochlic matrix, and to verify something's Cox-Becker graph is also not very easy. We have to check all the sets of all the cliques that sum to identity, so it's very hard. And but on the other hand, if we have some graphs with the separations, we can construct those projective Cox-Becker graphs. And the Cox-Becker graphs are quite interesting to physicists. They like them, they construct more of them, and the smaller they are, the better. So they have like this is an interesting result by itself. And also it is good to have characterization and to find this connection between A, chromatic number separations, and B, projective Cox-Becker graphs, and just Cox-Becker sets, which are very, very quantum. Okay. So that's what we've got, and so what we can remember from this talk is that, well, projective Cox-Becker graphs are good and they're useful for the examples where alpha and alpha q are different, or chi and chi q are different. So these are very nice. Also, it would be nice to know what other examples exist with the separation between alpha and alpha q. Preferably small, because it's still not known if the graph on 24 vertices of that there's a Pio-Bessan studied is the smallest one with the separation. So maybe somebody can find a smaller one, that would be good. In general, it's interesting to know about more infinite families or just other examples. And also when alpha and alpha q are equal, just just to be able to find alpha Q is good. And as I said, knowing when alpha Q is different reduces the surge a bit for the graphs where alpha and alpha Q are strictly different. Okay, and also Matisse Robertson had this example that we have homomorphism between the graphs if and only if some condition holds. Well, with the same condition holds in quantum case for the quantum homomorphism and quantum independence number. So in general, like when we had an apex graph, that getting an apex vertex will not change independence and quantum independence number. What other results hold both for alpha and alpha Q? There are any examples. That's nice. That's interesting, and that's a good starting point, because once you have a result for alpha, then that's already something to start with. You can prove it for alpha Q or no. And because there are not many ways to estimate alpha Q right now, and we are looking for, if we know it, it would be easy. Having other bound is always helpful. Yeah, we have inertia bound, quantum inertia bound, lower theta bound, ratio bound, anything else. Everything's welcome. Okay, and that's it. Thank you so much for your attention. Here I have the list of literature that we used. You can see some papers from quantum information. There graph theory papers, Logiska papers, Scarpa thesis, Susan thesis, etc. Lots of literature. You can look at it more if you're interested. But okay, thank you for attention.
Thank you very much, Mariia. Are there questions?
This is more a comment, I guess, than a question. But regarding other examples, probably you already know about this, but there's an example also by Teresa Piovesan, where there's a certain graph on 18 vertices that has alpha equal to alpha Q. But if you take 2 copies of it, then alpha Q becomes more than twice what alpha Q was originally. So it's not smaller because it's 36 vertices if you take 2 copies, but just 1 copy is 18 vertices.
Nice.
And it's also interesting that somehow alpha Q doesn't just double when you take the 2 copies. That's pretty weird.
Thank you.
So, yeah, I think it's like the line graph of the line graph of K33. I guess another comment, you asked about these bounds on alpha Q. So obviously there's Loess theta, and one way of defining Loess theta is that you assign a projection to every vertex so that adjacent vertices get orthogonal projections, and then you want to maximize the maximum eigenvalue of the sum of these projections. It's normally written slightly differently. It's written like you assign just the unit vector, but it's the same.
You want your projections to be rank 1, no?
No, you don't need to. It won't make any difference if you restrict to rank 1 or not rank 1. Is what happens, because in the end, I mean, in the vector formulation, you have this other vector, like this handle vector, right?
Yeah.
That you're taking inner product squared with everywhere. But actually, this vector is just a maximum eigenvector for the sum of the projections. And so if you have higher rank projections, you can just replace every projection with like the thing that it projects that vector onto. So anyways, okay, so you can write it as this sort of maximizing this max eigenvalue, but you could also try to maximize the min eigenvalue. And this is actually still an upper bound on alpha Q. This probably is, well, this should be very hard to compute, actually. So there are reasons why this should be essentially undecidable, I think, barring some technical details, I think. But it's another interesting bound, and it's related to this projective packing number, which I guess is in the paper with Laura, or it's in my thesis, or both, I can't remember, and that's just taking the average eigenvalue. So, and I don't know if always taking the min eigenvalue, if optimizing the min eigenvalue gives you the same thing as optimizing the average eigenvalue, or if it can sometimes give you a better bound.
Interesting.
Yeah.
Are there other questions?
Does something nice happen? So you had like these two products. Does something nice happen if you consider the strong product instead of your two other products?
Probably, if you look into it. I haven't, but it's a good question to study other products just besides the one that exists. Oh yeah, homomorphic product was motivated by the adjacency rule. Cartesian product came up because because you can say something about independence number in that case. If you use other products, maybe you can also say something independent about the independence number. So maybe that will help. Yeah.
I mean, I was just wondering because you have these theorems recently that say,
That's a
strong
good
product
question.
structure theorem stuff, and then you could say something about strong products, then maybe you could say something about tree width, and you could get bounds on quantum independence.
Yeah, that's true. Yeah. Yeah, if you can prove similar results for the quantum number, that would be good. Yeah. Thanks.
I also have a question. So your graph on 120 vertices, G120. So do you know that it is not a Calligraph? Or
Yeah, Sage told me.
okay. Of S5 or not a Calligraph of any other group as well?
No, not a Calligraph in general.
Okay.
Yeah. Because we didn't construct it, we didn't require it to be exactly a Calligraph. We just wanted the adjacency on the transpositions to hold to be in particular connection set. But for the other vertices, no, we just the orthogonality graph of the resulting vectors that we got.
But what was its automorphism group? What is the order? Do you remember how big it was?
No, I don't remember it. No.
Okay.
I can give you a graphic
Thanks.
string at some point. I think I have it still somewhere.
Oh yeah, that'd be great. Thanks.
Yeah, it's somewhere. Yeah.